The stream is about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause the stream is about to start. Get ready wherever you are, 'cause the stream is about to start. Hello, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is to improve the computation of RMS. What are we doing here? What is RMS? What the hell is going on? Here is a quick recap. We are working on a series of audio effects, real-time audio processors in REAPER using the JSFX language. We are developing a library, but also working on some effects. Right now we are working on this notion of an auto mixer, which helps you mix automatically multiple microphones that may be open in the same room. So perhaps in an interview, a roundtable kind of situation. And it's something that you can use for post-processing when you're editing a podcast, for instance. But you can also use it in real time. So if you have an event with multiple microphones on a podium, you can use an auto mixer. You can use this auto mixer that we are working on, the second version, right? We are working on the second version of this. You can use the first version of this already in this kind of live setting. And one of the things that we need for an auto mixer is to compute the notion of RMS, which is, given an audio signal, a rough estimation of loudness. And this is necessary for the inner workings of the auto mixer, but we will not get into that. We will just focus on the computation of RMS itself, which on the surface is something relatively straightforward because the formula that you use to compute RMS is in the name. You take the squares of samples, you take the mean of a bunch of squares, and you take the square root of that mean. So on the surface, this is straightforward, but when you get into the details, it gets tricky. Most things do. It seems like in audio programming, it's always like that. And John from Toucan Studios is here. Hello, it's great to have you here. I hope you enjoyed today's session. It will not be about user interfaces like it was the last time you were here, but I hope it's fun nonetheless. Right, so I wrote this very rudimentary, but at least performant implementation of RMS, and that's what is in the library right now. And that's what we are using on this first attempt, this prototype of AutoMixer 2.0. And then Tail, our guide and savior, Tail, sent me an email pointing out two issues. Well, pointing out more issues. I am going to talk about two of them today. And some of the other ones I don't think we will address today. We will address them at some point. Anyway, these two issues are quite deep and interesting, and the fix is relatively straightforward. It's just one line of code for this one, and for that one, it is just a couple lines of code. It's a super clever idea. I love this one. But I want to explain everything that goes into this one-line fix, and the issue that we are fixing here is it's very subtle. Oh, the whole gang is here. Hello, Tail. I am addressing your concerns today. We are going to deal with floating point arithmetic errors and rounding and blah, blah, blah. And hello, Bo. I'm doing okay. I hope that you are too. I hope that you are feeling better today. All right, so let's dive into this first issue. We want to make the RMS computation relatively fast. I think that there is one faster method, but it loses precision. I don't really like it. There is a video about it from about 2 years ago in my channel if you're interested. It has to do with an exponentially moving average, an exponentially weighted moving average. We are not using that. We are simply just using the definition of RMS, and there is one clever little trick that we use to make things relatively fast, and that is instead of computing the squares of the sample, so let's say that we want an RMS of the latest 1,000 samples. We don't compute the square of the latest 1,000 samples and add them up every time. And when the next sample comes in, we add all of them together again. And that is because let's say that there is sample 0, sample 1, sample 2, sample 3, and we are at this point. So at this point, suppose that we would like not the RMS of the last 1,000 samples, the RMS of the last 4 samples will do for us for this small example. So in that case, we would need to add all of these, and we would divide the result by 4. Of course, for each of these, we would be taking the square, and then we would take the square root of the whole thing. That's how you compute RMS, right? Then the next sample comes in, and then this one goes out, falls out of the window because it is too old. And you take the square of sample 4. Not the square root, the square. Now, we don't want to compute the squares of these guys over and over because the square of sample 1 here and the square of sample 1 there is the same number. Why would we compute this again when this next sample comes in, and compute it again when the next sample comes in, and compute it again on the next sample? It doesn't make sense, right? The square of a number will be the same, so we don't compute that square over and over. Also, note that this addition occurs twice, or I guess these additions occur twice. And they are going to be the same number. They're going to have the same result. So we have this clever little trick where we don't keep adding all of these things up over and over. Instead, we have this variable that we call running sum of squares. And that's how we do this. We take that running sum of squares and we divide by the number of samples and take the square root, and that's our RMS. When the next sample comes in, we update the running sum of squares. So we note that this oldest sample is going to fall out of the window because it became too old. We want the latest 4 samples, and this is not one of the latest 4 samples. So we want to drop this. So what do? We take the last running sum of squares and we update it by removing the guy that fell out of the window and adding the guy that just arrived. And then we can replace this here. So we changed something that used to do 1, 2, 3. And of course, this is a small example, so this would be doing 1,000 additions. We substituted something that would be doing 1,000 additions over and over with 1 subtraction and 1 addition. That's a huge win. In my video from 2 years ago, I compared the performance of this running sum of squares idea and the just naive implementation where you add all of these things up over and over. The difference is the biggest difference you can imagine. One doesn't run at all. It lags, it takes a lot of CPU. And the other is almost no CPU at all because it's just a bunch of additions and subtractions, not thousands of additions and subtractions. All is good until you realize that these are floating point numbers. They are not mathematical numbers. So taking something and adding it, then subtracting it back, does not necessarily get you back to where you started. So x plus y minus y is almost, but may not be the same as x. So it's probably very close to x, but not quite the same, because addition and subtraction introduce all sorts of errors in floating point numbers. Now, in practice, as far as I can tell, this is not a big issue. In my original AutoMixer and in plenty of other plugins, people compute RMS in this way, and they don't worry about these edge cases that we're going to get into in today's stream. It's mostly fine. I have never heard a complaint. But there are some things that we can do to improve on this that are so cheap that we might as well go ahead and do them. And that's what we are here for. So, what is one of the potential issues that we would run into? Because if we get to an x that is similar to our original one, no one will notice. It will be fine. But the problem is that these errors, these slight errors, accumulate over time. This running sum of squares will keep accumulating these errors over time. And what happens, for instance, if our x is 0.1 and then we add 0.3, subtract 0.3, and this is not what is really going to happen with these values, they're hypothetical, but what happens if instead of giving us back 0.1, because of errors that accumulated over time, we get minus 0.1? It could happen, probably not with such big values as 0.1 and 0.3, but with very small values, you could get to negative numbers there. And what do we do with these sums of squares? We divide by a number, and that's okay, and then we take the square root. So if we divide this by 4, that's okay, we'll get that number. And I cannot do arithmetic to save my life. So that's why I use the calculator for the simplest stuff. So we would get this number, and then we would try to take the square root of a negative number. Would you imagine that? Taking the square root of a negative number. That's a problem. Now, in mathematics, this is undefined. In many programming languages, this is an error. Your program would halt, and it would show an error to the user, perhaps. But not in JSFX. Let's see what JSFX do, because JSFX are bulletproof. There is nothing you can do that will stop JSFX from running. So I have a test effect that I use to play around with stuff. Why is this? Why is there a syntax error? Oh, I guess there is a syntax error in my library because I'm in the middle of writing stuff. Anyway, let's not import the library, and let's just take the square root of minus 0.1. So this should be undefined, or I guess if you are willing to go with complex numbers, then this would be a complex number. But that's too complex for me. I'm a simple person. So this just returns. Okay, you can never stop JSFX, can you? If you take the square root of a negative number, it gives you the square root of that positive number. It takes the absolute value of that number. Am I right? I think I'm right. Here I'm showing my JavaScript ways. Hey, there you go. So yeah, it is just taking the absolute of the negative number you're feeding in and giving you the square root of that. So perhaps that's why no one ever complained, because in my other implementations, I just had this perhaps happening, and then JSFX would patch the problem for me, would give me some result, and I would run with it. And this is all fine and good if you know what you're doing, but I didn't. I didn't know what I was doing. I was just lucky that it happened to work this way? Well, and it's an issue actually if you think about it, now that I'm thinking this through. It's actually an issue that it does that, because not an issue that JSFX does this. It's great that JSFX is trying to fix my mistake somehow. But the problem is we are at 0.1 because of all these errors that accumulated. Oh, I no longer have the example. But because of all these errors that accumulated, I am at minus 0.1. And this is way off. And if I say that, okay, I'm just going to take the absolute number, I'm even further from the truth. The truth was supposed to be 0, I guess. So in this case, we don't want to take, not in general, but in our particular application, computing RMS, we don't want to simply take the absolute value. We want to truncate this to 0. If it is negative, then truncate it to 0. That's what's up. And this is the single line that changes. That is the simplest thing. Let's find where we are updating the running sum of squares. And that's right here. Then let's rewrite it this way. And then let's take the maximum between 0 and that. So if the number is 0, or if this number is 0 or greater than 0, the maximum between 0 and that will be that. But if the number is negative, then the maximum between 0 and that will be 0. We are truncating this number. I think that we even have an auxiliary function that may help this read better. I think it is something like clip. Yeah, that's true, but clip also takes a maximum value that I don't want to have. So I'll just continue with this. And there you go. This is a single line that changes, but it fixes everything, because now the running sum of squares, if there is some sort of error that gets accumulated over this addition and subtraction, then the error at least will get us some non-negative number. And then moving forward, when we take the square root of the running sum of squares, we will, or running sum of squares divided by something, at least we will be taking the square root of a non-negative number. And this is closer to the right thing. And even if, I would say that even if for this particular application, we didn't want to truncate the number, but just take the absolute number, perhaps that would be okay. Depending on the application, taking the absolute number is okay. I still think I would write it as something like this, just because I want to communicate the intent of this really is the way I am dealing with the approximations and the errors that accumulate. Even if it's implied, even if square root in JSFX happens to have this effect, I still want to document that this is my intent. It wasn't by accident. So now I'm communicating another intent. But anyway, this is the fix. So preventing negative numbers. And I don't have any tests for this. In my tests, I'm working with really large numbers. They are not even samples, right? I'm just taking numbers like 2 and 3. So floating point errors will not play a role into this. But still, I just want to make sure that I didn't break anything. So I'm going to rerun my tests. And I do have a problem in my syntax here. What could be the problem? Is it perhaps the comments I added? I think I would just drop this into a separate file. Especially because this has desk, and that's a magic word in JSFX. It may be breaking things, and these are magic words too. So even though the syntax highlighter on this Visual Studio Code extension was highlighting the whole thing as a comment, I think that in fact the parser in JSFX is actually looking at these anchors and then messing everything up. Okay, the puny test that we have is still passing. Okay, so I fixed the problem without having a proper test. Shame on me. Or not quite. I don't have an automated test, so shame on me, but at least Tail tested this and he proved that it was possible to get to negative numbers. So I trust Tail with my life. When it comes to audio programming, I wouldn't trust him on other things, perhaps. I don't know. Yeah, this is exactly what I want. Oh, great. It comes and goes, but great. I did some tests a while back with infinite impulse response and whole RMS. The whole sounded surprisingly transparent. JSFX also has triple equals. Oops, I bumped into your ear. Sorry about that. Yeah, it also has triple equals, and it's quite interesting. In JavaScript, triple equals is not only these values need to coerce into the same thing, but they also need to be the same type. So you're not allowed to do coercions. And in JSFX, it means something completely different. It means these two numbers are exactly the same. If you just have two equal signs, it means these numbers are relatively close. The delta is very small. But three triple equals means exactly the same number. Let me see if I can show this, because it's kind of an odd property of JSFX and it's kind of cute. So let's take two very small numbers. Did I overflow a floating point number? I think I did, because it evaluates to 0. So I have to have fewer zeros here. Hey, there you go. No overflow. And then is this equal to that? Hey, it is equal to that. But hang on, JSFX, is it really equal? No, it's not. There you go. That's the triple equals. Nothing. I guess it is sort of related in the sense that it's a stricter notion of equality, but it has nothing to do with the notion of types, because in JSFX there is only one type. The type is double floating point number, 64-bit. So yeah, this is what triple equals means in JSFX. And in most cases, people use double equals. I think it's okay, even though I think that 2 equals, because it has this magic property of looking at the delta, it probably has to translate this into something like that, where this is your threshold of equality. So this is probably slower than the literal triple equals check, where you can just look at the numbers and compare them bit by bit and you're out of the question. So I think that this the two equal signs is probably slower because it has to do more stuff, while the 3 equal signs is probably faster because it can just compare bits. But I don't know. I haven't really measured, and I see most people using 2 equal signs, and that's what I use too. But if people know what is faster, 2 or 3, or if there are other implications, then I would love to hear about it. Triple equals to find out if you're running in the problem we are having here. Hello, M9. I am doing good. Yeah, and the way that Theo explained it to me in the email that he was able to test and get to negative numbers was to have some numbers, some samples coming in, and then feed some silence for a bunch of time, and then the whole window of the RMS computation would pass by. And perhaps there would be even some very small samples that are non-zero because of the denormalization, and maybe that would also help throw off the additions. I don't know. Anyway, we took care of this first issue. Now let's get to the second issue. There are 3 of them, okay? 3 of them. We worked on the first one. The second issue is to improve even further on this notion of errors accumulate over time. So they are very small errors. No one is probably going to hear any of these errors, but still, errors are going to accumulate on this variable over time. And if you leave the plugin running for a long time, then these errors will just keep growing and growing. And that's bad. And I read in forums before a solution for this. And that is, from time to time, you discard the running sum of squares and recompute it from scratch. Because we need to have this thing that is the old value that fell out of the window, because we need to store that anyway, it is relatively inexpensive to go ahead and recompute the running sum of squares, because you have the values to begin with, you just have to add them back. And that's okay. From time to time, you pay the price of adding a bunch of numbers, and then because you discarded the running sum of squares and started from scratch, you discarded the errors along the way, and you have a clean slate. That's okay, but it's not great. It's more code to write. I don't love the idea that from time to time there is this extra CPU that you need. And it's not unheard of. Like when you're computing FFTs, from time to time you fill in the FFT buffer and then you do FFTs, which are more expensive. So it's not unheard of that from time to time you have this extra load on the plugin. But for something as simple as RMS, I never really saw a point, especially because I didn't run into the error in the first place. But then Tail showed me this solution that I have never seen anywhere else, and it's so clever that I have to implement this. It is the nicest solution ever. Here is how this works. And this is the implementation, by the way. If I am not explaining something right, or if I cannot implement it right first try, I have the implementation that Tail provided me, and I can just take a peek. But anyway, I'll try to explain what the idea is. Oh, it is more like this. There you go. So you have your running sum of squares, and to update it, you take the existing one, you subtract the old one, you add the new one. Same story, right? Here is the cute little trick. On the side, besides keeping this running sum of squares, you do keep this running sum of squares as usual, but on the side, you also keep a second running sum of squares. And for this one, I guess I'm going to rename this. It would be just the sample that just came in. You just add this. So this is a running sum of squares that is taking in account the window. And this is a running sum of squares that does not take in account the window. It just accumulates all the samples as they come in. And of course, this number is going to be bounded in size, but this number is just going to grow larger and larger and larger and larger. But that's not all. We also have this notion of the size of the window. How many samples are we computing the RMS of? In my example here, I guess 4 samples. So here is the magic. there is this notion of the window size, and there is also the notion of write index that is just a circular counter. It is a magic circular counter. In our actual implementation, this circular counter is hidden within this circular buffer, but we can always access that index if we want. And that's our write index. And this write index starts at, so this circular buffer here, it is where we store the samples. It's actually not the samples, it's the square of the samples. Never mind that. We are storing these guys over here on this circular buffer. And when a sample falls out of the window, it falls out of this circular buffer. And this is the write index into that circular buffer. So we have a circular buffer of 4 slots, and then our write index is 0, 1, 2, 3, 0, 1, 2, 3. When it gets to the end, it grabs back. So here's what we do. We can ask if the write index is, let's say, 0, and the write index is going to be 0 when we get to window size, and then it rips back. So if our write index is equal to 0, here's what we do. We are going to swap the two running sum of squares. So now, by this point, when we get here, it means that this running sum of squares. So, hang on. Think about the case where the plugin has just loaded. It has just loaded. So this running sum of squares, we will be subtracting a bunch of zeros. That's okay. And it will be adding the samples that just came in. And this is also adding the samples that just came in. So when the first time that the write index wraps around, when the plugin has just loaded, the first time that the write index has wrapped around, these two values are the same, right? So it's okay if I just say something like this. And then I zero this out. Now, think about the second time that we are running around this. So these two values are the same. I didn't change the running sum of squares in any way. And then the sample 0, now that we are on the second window of audio, this is no longer 0. And we are subtracting some non-zero number. We are accumulating those errors, and we are accumulating those errors over the next window. And this guy is no longer the same as that one, because this one is really the running sum of the squares of the last 4 samples, while this one started from scratch. So this one is just the latest 1 sample, the latest 2 samples, the latest 3 samples. When it gets to the latest 4 samples, supposedly these two values are the same, except for the rounding errors and the things that we are trying to get rid of. These two values should be the same because we have just accumulated a whole window. So this now contains a whole window, and that one subtracted the old samples and has a whole new window in there. So again, we just swap the two. We say that this guy that has no errors because it was fresh, so it has no errors. Now this guy is equal to that guy. And we start from scratch again. So we don't need to look at the clock and check, I haven't computed running sum of squares in a while. Probably some error has accumulated. Let me scrap running sum of squares and recompute it from scratch. You don't have to look at the clock. You don't have to recompute everything from scratch. The only price you have to pay is one addition, one comparison, and from time to time, a couple assignments. Those are really cheap compared to looking at the clock, adding a bunch of samples from time to time. I guess the addition, the extra addition is inevitable, but at least we are smearing that cost over time. We are not paying it all at once. Yeah, that's the only advantage, really. It is inevitable. If you want to get rid of the error, you have to start from scratch and accumulate again. So it's inevitable that you would do one extra addition here. But at least you're smearing that cost over time. You're not having to look at the... I guess this is amounts the same as looking at the clock. So in the end, this is just an elegant way of implementing the idea of looking at the clock. I find that this is beautiful. It's just one of those things that is like brilliant. Infinite impulse response based RMS that is same with whole based RMS. Dirty buffers related to, yeah, I guess. I would recompute every block, I guess, because I don't like to solve problems if they're small enough. Yeah, we are solving a problem that not that many people will run into. I would guess no one is ever going to run into this. But anyway, very few people are going to run into this, if ever. But it is such a nice concept. These two running sums and the swapping and the resetting and all of that is just so nice. We have to do it. And because I am too lazy to make such clever things. That's why I make good friends. Lol, yes, I understand. I try to make it work first, then optimize later. Yeah, that's exactly the approach I took, by the way. We have a working auto mixer. It doesn't have all the features that we want to implement, but it is working. We saw that yesterday, and we have a working RMS computer and everything. What do you mean by rounding errors? What I mean by rounding errors is hang on, let me see if I can remember this URL. It is 0.1 plus 0.2 equals 0.3, and there is a URL that is super long and it's kind of fun. Yeah, I think it's this one. That one. This is what I mean by rounding errors. It's not really rounding that we are talking about here. It's not really rounding. It's just when you do operations like addition, subtraction in floating point numbers, all sorts of weird things can happen. For instance, if you add 0.1 and 0.2, you will not get 0.3. You will get this number. And this little error, it's not a rounding error, I don't think, but it is a small error. And this small error occurs because of the way that floating point computation has to be implemented in the CPU so that it is fast and all sorts of other properties. But anyway, this small error is super small, right? You probably would say this is like what? Minus 1000 dB. It doesn't matter. But these accumulate when you keep adding them in the way that we are adding stuff in the running sum of squares. So that's what I mean. Hello, Rafael. Hello, Aria. Yes, I am having an amazing day. I just bought one of those electric scooters. They're so much fun. I am scooting when I am not here streaming or working or sleeping. I guess I should stop sleeping and scoot more around the town. It's such fun. Electric scooters. I'm loving them. And it's summer here. It's beautiful. It's lovely. I'm having an amazing day. Yes. Yeah, okay. I thought people use double types to get rid of floating errors. Well, in JSFX, we don't have an option. We can only use doubles. When we are doing C++, we can use floating points that are 32-bit, but in JSFX, it's only doubles. And for the most part, it's okay. Floating point errors are so small, especially with doubles. They're small enough, but you're not getting rid of floating point errors, okay? You're not getting rid of those. So if you're doing something that does not stand any kind of error like this, and you're willing to pay the price of slower computation, you should not be using floating point numbers at all. Not 32-bit, not 64-bit, doubles, it doesn't matter. Don't use floating point numbers if you care about precision and you can pay the price of slower computation. When you're dealing with audio, we don't care about precision that much, because if the noise is about at minus 100 dB, minus 500 dB, it doesn't matter. Perhaps minus 100 matters, but minus 500 certainly doesn't. So in audio, we tend to use floating points because we don't care about precision to that point, and we cannot pay the price of slow computation. We have to deliver those samples or we will hear artifacts. But when you're dealing with like money, you do care about floating point errors, and you don't use floating points. You use fixed point numbers and big integers and that sort of thing. I could stream on my scooter. How about that? I would be scooting and programming and streaming and probably getting hit by a car. Yeah. So yeah, that's a good question, Bo. Aria, did you get your, I guess you had like some sort of container that you were moving, and did it arrive? Did you get your furniture and your gear and your computer? And minus 100 dB is analog warmth. Well, let me tell you, I am doing some analog stuff. I don't know if you caught that. You probably didn't because you were like living your life. But I got some equipment, some components, and I started fiddling with analog gear. It's such fun to create stuff with your hands and then hear it. It's such fun. Oh, good luck with that. Oh, that's the worst time in our lives, right? When we are moving and assembling IKEA furniture. I freaking hate that. All right, will I be able to implement this in 15 minutes? I sure hope so. The idea is fresh in our heads. Let's go ahead and bite the bullet and do this. I'll call this the secondary running sum of squares. Or maybe even better, like a clean, as in no rounding, no floating point arithmetic errors. It's a clean running sum of squares. And I guess I will put this as a suffix. There you go. Now the data structure has 6 fields, 0 to 5, and we need to initialize the running sum of squares clean to 0. Then when we add samples, nothing changes. Remember that adding a sample takes in account multiple channels. So it's just accumulating the running sum of squares here. And sorry, not the running sum of squares. It's just accumulating one of these squares. And that's because we are not simply taking the square of a sample, the square of the next sample. We are actually taking into account multiple channels, and we are adding them up at the level of squares, which, by the way, on this sample code here that Tail sent me, just so you know, Tail, because I think you were watching, this line is not exactly how you should be doing things, because here you are accumulating stuff from different channels at the linear level and then taking the square. And think about the case in which these two are exactly out of in inverse polarity. They're going to cancel out, they're going to null, but you still hear from your headphones or from your monitors, you're still going to hear sound. They're not going to perfectly cancel. So you don't want to compute RMS on the linear level, you want to compute it at the square level. So the way you should do this is take the square here and take the square there. Now, you may already know this, and it's not a big deal because you were trying to show something else in this example, but it's just something to be aware of. It's a mistake that many people make. In fact, it's a mistake that the original implementation of the auto mixer that comes with Repack by Corey, I forget his last name. Corey created, maybe I have here the auto mixer, the original auto mixer. Yeah, Corey Skogin. Great fellow, such an inspiration for me because it was this plugin that got me started in JSFX. Anyway, the way that he was doing this computation in the original implementation of the auto mixer was the wrong way, this way. And then it was my contribution, my first contribution to some JSFX to fix this. I don't know if it is documented here anywhere, but hey, there you go. Now it is accumulating stuff after taking the squares. And when you take the squares, the values are no longer going to null, because if this is 1 and this is -1, the squares are going to be 1 and 1. So they're going to accumulate with positive numbers, and they're going to come out with a positive number instead of canceling out. Anyhow, this is us doing the exact same thing over here. And then we get to this part where we advance. And when we advance, it means we have accumulated the samples for all the channels, and we are ready to move on to the next part, which looks like this part, this stuff. So let's get into that. Running sum of squares, and also the clean version. Aria, if you're still watching and if you are interested in streaming together at some point, if you have your gear, then that's better. But if you don't, you can always just call in with your cell phone and we can chat and we can have a stream together. So if you're interested, let me know. But I know that you are probably very busy at this point. But some escapism can never hurt. Escapism is what we all need after this pandemic and everything, or in the middle of this pandemic and everything. Okay, so this is going to change and that is going to change. So let's put a copy here and there. So how do we update the running sum of squares with this formula? How do we compute their clean version? We just add the square in progress. We don't subtract that. And because we are not subtracting stuff, there is no chance of us getting negative numbers. So this max is unnecessary. Because floating point errors are weird, but as far as I know, if you add strictly non-negative numbers, you are never going to get into a negative number, except for overflows, but never mind those. And I guess even overflows give you back infinity or not a number. They don't give you back negative numbers. Those are weird. And I guess I'm going to change the order of these variables just because I want to have this as like take the original thing, subtract the old stuff, add in the new stuff. Okay, so that's how we compute the clean running sum of squares. Now, let's do the swap if necessary. And how do I know that I need to do the swap? I guess one way is to just check what is the current index on this circular buffer. If the current index is 0, it means I just wrapped around and it's time for me to swap. And on the very first sample, this index will be 0 and it's not yet time for me to swap, but we are just swapping zeros. It doesn't matter. So let's add another variable here. And that's our right index. Oh, and I forgot to check which came first. It's length and then right index. So let's do length and squares right index. Do I have some sort of auxiliary variable for this? Or auxiliary function to get this? No, I do not. So we have our squares, then it's length and right index. We have our squares, then it's length and right index. Seems about right. And we are not changing the squares in the length or the right index. We are pushing to it, all right, but we are not changing its base address, so they don't need to appear down here. Okay, so we can check. Is the right index equals to 0? If so, it's time to swap. And that's all there is to it. Cool. Does it work? Let's review what we changed. Looks okay to me. How can I test if this works? First of all, I can just run the tests, but not this file. The other one. Oh, the tests fail. Cool. Did I forget to say that some variable is local? I did not. What is the result of the tests? Let's dive into the library, find RMS test, and then run this by hand. So this is going to allocate a place in memory. So this number is just the place in memory. It doesn't mean anything. Then we add, and this is just returning me the square. So that's fine. And then this is supposed to return to me the additions of the two squares. So this returns to me the running sum of squares. And that's 13. Because it is 4 plus 9. That's 13. Then advance is going to return to me the current RMS, which is, let's think about this. So we have 4 plus 9, that's 13. We have to divide this by the number of channels and divide the result by the number of samples we are accumulating. We are accumulating 3 of them. Then we need to take the square root of the result. In this case, the mean takes in account not only the number of samples or the number of squares, but also the number of channels. Yeah, that's the correct thing to do. Another way of writing this is something like this, which I kind of prefer. Anyway, we are supposed to get 1.47. Yeah, that seems about right. 1.4719. 1.4719. What are we getting? We are getting 0. And 0. Why would that be? Let's see if my friends caught my mistake. Nice. I may get a broken analog mixer from work. I thought it would be fun to open it on a... I am so in for that. I will be watching. Instead of resetting the buffer, can you just divide the buffer by 2, cut the error in half before adding the next sample? I'm tempted to say no. Because if you're dividing the buffer by half, either you're going to have to multiply by 2 later to compensate, or your final result will be wrong, right? So when you divide the error, you're not making the problem any better. You're probably making the absolute error smaller, And that may be advantageous when you're accumulating samples, but I don't know. I guess in general, the rule of thumb should be the fewer operations, the better, because each operation is going to add its own error to the equation. Even dividing by 2, we will add its own error. And it's slower. The more operations you do, the slower it becomes. So I don't know. Perhaps. Rafael asks, a little question from another matter. That the lay plugin you and Aria were developing is functional with this version of the library? No, the library has updated in many ways, and that plugin is probably not working with this version. It is working with the version that it was developed with. Yeah, you're probably getting an error while trying to use it because many things changed, not only in the implementation, but also in the interface. So, and when I say interface, I don't mean user interface, I mean the interface between the library and the effect using the library. We changed the function names, we changed the arguments. It's not going to work. I think it's not far from working, but I don't think it's going to exactly work. We will get to that plugin again at some point and finalize it. I still have that grandiose view for a waveform that is falling and kicking on the floor. We'll get there. We have a long-term plan for developing effects here. My plan is to do this for a good amount of years here. We'll get back to that effect. Yeah, I know I was assuming the input was mono, but Reaper has no mono tracks. Fair enough. For what it's worth, the real issue with accumulated errors is that at some point your sum will be stuck at some very small value. This could be fine. Or not. And this could be a negative value, or not. Yeah, this getting stuck into a very small value, in our case, I don't think would be the biggest issue. And in fact, we take care of this in the auto mixer. We take care of this problem of very small values. I guess it's a different kind of problem. But in our current implementation of the auto mixer, we have this sum of all RMSs thing. This could be 0 if all the RMSs are 0 because all the channels are being fed complete silence. Well, not really because of the denormalization protection in JSFX, but you get my point. And I'm adding a very small number here. This is at least guaranteed to be non-negative now that we implemented that fix. So this will be non-negative. So we are adding a very small number here just to make this whole thing not divide by 0. Home now just because I got code. Oh no, fuck. Sorry. I hope you recover fast. Oh no, fuck. Hope you all recover fast. This thing is spreading. Sorry to hear that. All right, okay, let's try to find the mistake. And the third problem we'll not get to today. What if we don't ever use the clean running sum of squares? What if we don't do this? Or I guess I can just do this. This will not use the running sum of squares clean. If I don't do it, is my test passing? It is. Oh, so it really has to do with this clean running sum of squares situation. Let's look at the running sum of squares by putting some debug variable here. And because I did not declare this variable as local, by default it is global, and then we see it on the right pane where we inspect variables. Debug is 0. Now, Does this make sense? I don't think so. Let's check the running sum of squares without the clean part. And I'm probably making some silly mistake where I have some wrong name somewhere or something. I don't think it's the algorithm that is poorly implemented. I think it's a silly typo somewhere. Okay, let's see. Yeah, the running sum of squares is 13 and the clean version is 0. So that's wrong. Oh, but it could be 0 because of this part. Let's not zero this out. Nope, it's still 0. What's up with that? Are my indices messed up? Doesn't seem to be. Am I allocating enough memory? 0, 1, 2, 3, 4, 5, 6 slots. Am I initializing stuff as I should? It seems like it. Yeah, that's right. Yeah, that's okay. What is this square in progress situation? Oh, I am zeroing the square in progress because I have just pushed. Oh, that is why. Okay. See, it was a silly reordering situation here. I'm going to finish this and then I'm going to look at the chat and then Tail will have figured it out 5 minutes ago and I'm a fool. That's what's up. That's what's gonna happen. Running sum of squares, blah, blah, blah. Then we push. So I think that this should be along with that. So we are updating this and we are updating that side by side. That's lovely. Then, oh, now that I'm pushing this here, this will trigger in a different, at a different point. Do I care? I don't, because I'm still using the window size just right, so I don't care. It's going to be one off. It's going to be even better, actually, because it's not going to trigger when the effect just loads. It's going to trigger one sample after that. But then I'm accumulating one sample extra besides what I should be accumulating. Yeah, I don't want to do that in that order. I probably want to do it like this. So now we are using the square in progress. And then we reset it. And we are using this, the clean running sum of squares, and then we reset it. These debuggers can go because I fixed the mistake. See, the tests are going to pass now, and I will be able to go out and scoot around the city. It will be great. Hey, the tests are passing. The stuck small sum happens if you mute a microphone because all the squared samples from that point on will be 0. Yeah, and in many situations you'll be doing post-production on a podcast, and some people like to gate or to even do some dynamic split and completely remove parts that are too silent. I'm not too keen on that. I don't do that. I prefer to have some room tone, but some people will just delete portions of the conversation altogether, which I think also throws off the auto mixer a little bit. But anyways, any kind of defeats the purpose. If you're using an auto mixer, you don't need to be that careful about removing the moments when the person isn't speaking. But anyway, It could be the case that people do that, and then you would end up in this situation where you have a bunch of zeros in a row. I read that the latest mutations are very contagious, but you don't get as sick. Yeah. We gotta make you a script for removing the effects and putting it back. Yeah, I could assign it to a keyboard shortcut, but I didn't. I could assign it to a keyboard shortcut, or I could have some sort of Arduino. Or actually a Raspberry Pi Pico. I really want to get one of those because they're so inexpensive. I don't know what to do with them though. But then I could have a button that is like a button that I press and then it loads my plugin on Reaper. Ha! Here's something I can do with a Raspberry Pi Pico. Yeah, more contagious, but I heard the same. Square in progress equals 0, question mark. Hey, Healy's Tale, finding the mistake 5 minutes before I do. Thank you, Tale. Thank you, Rafael, Aria, Bo, M9, and John. And yeah, thank you everyone who was here on the chat joining me on this one. It was fun. Next time, hopefully tomorrow. So I fixed the thing, so might as well commit it. Hey, it was a simple line change. Good stuff. So tomorrow we'll be back and we'll be looking at this. We'll be allowing you to change the window length, which is essential for the auto mixer because we want to let the user change the window length. So that's what's up for tomorrow. Yeah, thank you everyone who was joining me on this ride. It's great to have you here with me. Take care. I wish that you all recover. And I see you back here tomorrow. A question. Could I have your on Discord for a while after this stream? You can have me on Discord after I scoot around town and get back. So write to me. I will get back to you as soon as I can. Oh, mild cold plus exhaustion doesn't sound great. Anyway, see you tomorrow. Thank you all. Have a good one. Bye. Thank you for watching the stream. You know how great it has been. Or maybe it sucked, and I am glad that you stuck with me. And soon we'll all be back together for some more coding or talking or chilling. The next time I'll be streaming.